Okay, so this is all well and good and interesting, and welcome everybody. I wanted to first of all talk about the final examination, which is on the ubiquitous sheet. See if I can get the sheet up. Yeah, there it is. Unfortunately, the time today kind of snuck up on me, so I apologize for being late, but better late than never, as somebody said. Okay, share screen. There we go. Okay, so what I wanted to see is if you had any questions on the homework as far as performing the operation. I had one here, but I decided not to do it. I'm sorry, I had a problem here and I decided to nix it. So you should have seen that nixing. So these are renumbered. Okay, the first one is kind of mixing some of your background. And this, I think, is where courses are fun, when you begin to mix what you've learned with what you've learned before. So that's what this is. So let x of t be a deterministic function whose Fourier transform is 0 for f greater than b, where b is the bandwidth. And this, of course, is referred to as a band-limited signal. And you all know, hopefully, from signal processing, that the sampling theorem says the second question. Unfortunately, I haven't been able to find an equation editor in Excel. They might have one, but I haven't found it. So x of t is equal to the sum of the samples, n over 2b times the sinc of 2bn, where the sinc of 2bn is, the sinc of t is equal to the sine of pi t over pi t. And we use that for a very specific reason, which I'll talk about just in a second. And so I'm going to ask you the question here. Suppose x of t is disturbed by zero mean additive white noise, E of t, and you have this new signal, y of t is equal to x of t plus E of t. This is a common model for adding noise to deterministic processes. So you have what you want, and then you have the noise, and y of t is what you get. So the power spectral density of the noise is S, that should be S sub E of F. So that E should be a subscript there, and it's equal to a constant because it's white noise. And we are going to assume again that it is zero mean, and consider the sum Z of t. What we're going to do now in the summation is that we are going to put y of t, samples of y of t, that is samples of the noisy signal, directly into the sampling theorem. So we generate a Z of t here. And this Z of t is not equal to y of t because clearly the white noise is no longer band limited. So we don't have to worry about it. We don't have to, well, we can't, we have to worry about it, but it's no longer band limited, and Z of t is not equal to y of t, where the samples came from, because there's going to be noise associated with it, and it's white noise, and it has arbitrarily large frequencies. And then the first thing I'd like you to show, which I think is pretty simple, is that Z of t is equal to x of t plus q of t. X of t is the original noiseless signal, and q of t is a stochastic process, as you can read right here. Q of t is a stochastic process, and I want you to provide the expression for q of t. This is just a couple lines, not a big deal. And then I would like to ask you, what is the autocorrelation and mean of q of t? In other words, Q of t is a stochastic process because it's interpolated with a bunch of values of samples of Z, which is the white noise. And then if Q of t is stationary in the wide sense, and I'll give you a hint, it is, then what is the power spectral density of Q of t? What is the power spectral density of, by the way, are you hearing me right? It just occurred to me.
I think
Dr.
that
Marks?
your microphone.
Yeah, when you moved your microphone, we can't hear you now.
Okay, let's.
Dr. Marks, I think when you moved your microphone, it made it to where we couldn't hear your voice anymore.
I know what I'm doing, believe it or not. Can you hear me now?
Yes.
Yes.
Okay, and I'm hoping that the quality of the audio is a little bit better. I do use a very nice microphone for recording Zoom meetings so that the audio will be better. So what you heard before, I think, was a little substandard in terms of the audio quality. Okay, thank you. Okay, okay, so again, if Q of T, if this interpolated noise is stationary in the wide sense, what's the power spectral density of Q and T? So this is going to be kind of a general problem. So if you're sampling a signal and the signal is accompanied by noise, and you can model this signal as noise and you interpolate it, what is the power spectral density of the interpolated noise? That's what we're asking for here. Now, I will tell you a few things about this. I'll elaborate just a little bit on this. By sharing my whiteboard here. You notice that the sink of T is equal to the sine of pi t over pi t. There's a reason for doing that, one of which is that the sink is very nice to remember. If we look at the integer values on the timeline as a function of time, this sink has a value of 1, and it goes down and it goes through all of the integers. So it goes through 1, 2, and 3. So it's beautiful in that sense. It's very nice. Now, many times you'll hear people talk about the sink and have it defined differently, but there's a beauty in defining it this way, one of which is this. The other thing is its Fourier transform is a rectangle function. So it's equal to 1 for f less than b, or less than 1/2, I'm sorry. And it's equal to 0 for f is greater than 1/2. And when it's equal to 1/2, nobody cares, right? Because 1/2 is an exact frequency which can never be measured. So the Fourier transform of this sink beautifully is a nice rectangle function, and we denote it. I denote it by this. That goes between minus 1/2 and 1/2 here. And it has a height of 1. So this is really good stuff, because it's very, where'd you go? Where'd you go? Where'd you go? There you went. So it's something which is very, very easy to remember. One of the interesting things about the sink is what you get, and you'll be using this maybe when you do the problem. Suppose that you take the sink and you multiply by itself. Can anybody by inspection tell me what the result is? Okay.
Would it just be like steeper and positive?
Give me a function to put here.
Sink squared?
No, that would be sink times sink. That's very close.
Oh, you said multiply. You meant convolve.
Oh, okay. Did I say multiply? I'm sorry, yeah. I meant convolve. Yes, I misspoke.
You convolve two sinks, you get a jink.
Try it. Nice try.
Do you get a sink?
You get a sink back. Isn't that interesting? You get a sink back. Why is that? Because a sink of T convolved with a sink is such that when we Fourier transform it, it Fourier transforms to a product, right? So it's this function times itself, isn't it? And this function times itself is the function. You're either multiplying 1 times 1 or 0 times 0. Doesn't matter. So therefore, this is the correct answer. A sink convolved with a sink is equal to a sink. A very curious result, I think. I do not understand why a sink convolved with a sink, at least in the time domain, is a sink. It doesn't have any intuitive feeling for me. But once I do it in the frequency domain and I apply the convolution theorem that the convolution in one domain is equal to multiplication in the other domain, it does make sense because a rectangle times a rectangle is equal to a rectangle. Okay. So I think that hopefully will help you out on that problem with the sampling theorem. Any questions on that?
No, but I'm glad we went over it because I found a mistake in my math.
Okay, well, good. That's the reason I went over that. That is one of the little tricky problems. One of the little tricky problems in solving that result. Okay, let's see what I would do if I was smart. Okay, there we go. So that will help you on C. Then I would ask you to do number 2, and this is the autocorrelation of a wide sense stationary stochastic process if x of t is given by this expression here. This should be a 1 over 1 plus t squared. So it's a bell-shaped curve, but it's a bell-shaped curve with really, really fat tails. First thing I'd like you to do is to evaluate the expected value of 5, expected value of 6. This shows the utility of the autocorrelation function in second order statistics, in that you should be able to compute this result very easily. And then if x of t is a current in amps through a 2 ohm resistor, what is the average power dissipated by the resistor in watts? Now, I think before we talked about 1 ohm resistors. Hey, let's be a little bit bold and go to a 2 ohm resistor here. And then we're going to pass x of t through an ideal low pass filter. So this is an ideal low pass filter with an abrupt brick wall cutoff at f is equal to 1 on both sides. Okay, and it's 0 otherwise, and the output is y of t. And then I'm asking you, what is the power spectral density of y of t after you've passed x of t through the low pass filter? And then D is, what is the average power dissipated by a 4 ohm resistor when y of t is the applied current in amps? So therefore, we run it through a 2 ohm resistor before, then we run it through a low pass filter, and then we run it through a 4 ohm resistor. And what is the average power dissipated by that resistor? That will tell you how much, if it's just a regular resistor, it tells you how much the resistor is going to heat up. If it's a light bulb, it's going to tell you how bright the light bulb is, because how much current is going through the filament. So we would just like to figure out what this is. Please do not forget units. Power has units, and we do all of this math and this hand waving, but sometimes we forget what the units are. And if the units are amps and the resistance is ohms, of course, the power is in watts.
Dr. Marks?
Yes.
For me and Adam and Theo, the Zoom had cut out and died, so we missed everything since you mentioned the 2 ohm resistor.
Since I mentioned the what?
The 2 ohm resistor.
Oh boy.
Oh no, I think we got to the parts. We were just starting part C.
Part C.
Talking about the
Okay.
That's correct. Yeah.
Okay. Well, yeah, I think you can read it. And that's what I did basically. We
Okay.
take the stochastic process, pass it through a low pass filter. Its frequency response is 1 for f less than 1. It's assumed to be a brick wall filter, and the low pass filter is assumed to pass all the frequencies with a value of 1 over the pass band. And we look at the output of that filter, and the output of the filter is y of t. And then we ask ourselves, what is the power spectral density of y of t? Something you should be able to figure out. Then in D, what is the average power dissipated by a 4 ohm resistor when y of t is the applied current in amps? So we have 4 amps. I'm sorry, we have X of t as amps going through a 2 ohm resistor. We pass it through a low pass filter and take the output of the low pass filter. We apply that same amperage to a 4 ohm resistor and ask what is the average power dissipated in that 4 ohm resistor. And my comment was, if it's a resistor, it'll tell you how much the resistor is going to heat up. And it's, I guess if it's a light bulb with a filament, it's going to tell you how bright the filament gets. Because it seems to me the more current you put through a filament, the brighter it's going to light up. And then I'm going to ask you the question, is the process mean ergodic? In other words, can you take the stochastic process with the autocorrelation given and compute the mean of the stochastic process by just looking at one long instantiation of the stochastic process? Okay. And we went over that. And so I think that this covers most of the stuff that we did in the filtering of stochastic processes. So this will be very good. Then I screwed up on the March 25th, take-home test. So I'd like you to redo that. And I changed the numbers to something more appropriate. Okay.
Dr. Marks,
Yes.
do you mean the March 23rd on that? The dollar problem?
Let's see. Actually, I mean both the 23rd and the 25th. Everybody's going to be mad at you. Sorry.
Oh, so you want us to do all the problems from that homework?
Yeah. In other words, let's go back and let's review it. March 23rd. No, I don't. Let's see. Come on. Yeah, I just want you to do the number 2 for the second one.
Okay, so number 2 on 23rd, and then the problem for number
Yes.
25.
Yes. And I think I changed that number. Let's see, 23rd.
Yeah, I think you changed the number on the 23rd, but not the 25th.
Yeah, I think that's correct as well.
Okay, I guess I did mean the 23rd. I'm sorry. Okay. Does anybody remember the television show that said the names have been changed to protect the innocent? You're all too young. Okay. Well, the numbers have been changed to protect the innocent. And that's me. So, okay. So that's the exam. Any questions?
I have a question. In problem 2B, you said that we did the same problem with 1 ohm resistor in class?
Yes.
Okay, perfect.
We've done it with 1 ohm. So I just don't want us to take granted every time you have a stochastic process, it goes through a 1 ohm resistor. This makes you think about this much more. It's not a big deal.
Okay, thank you.
Okay. So that is good. The other thing that I did is everybody was having a challenge with this one, so I went ahead and did this. Did anybody get this homework of April 6th? You were going to look at it. What's that?
Only with help of the solution. I did it incorrectly
Okay.
the first time.
Only with help with the solution, yeah. So,
And Adam to help me think through it.
Okay, that's good. Yeah, the solution, where's the solution? Yeah, it starts here. There's a link to a Google Docs here. So you can go through this solution and you can see what the result is. So it worked out to be pretty well. I think those of you that have had some signal processing recently, like the multidimensional class or undergraduate 335, are probably more akin to this Fourier analysis stuff. So this is kind of assumed to be a background that is needed for this course. So if it's new to you, well, it's about time to it's about time to get up to date.
Up on it.
Yeah, because Fourier analysis is fundamental, I think, in almost all elements of electrical engineering. Fourier analysis, I think, overall is the second most used mathematical tool. The first one is the differential equation. I mean, people over in our math department are still solving weird differential equations, which are really strange, nonlinear, time variant, and other things. And so differential equations are used frequently. Fourier analysis is used possibly the second most frequently. Okay, so I did want to point out that these solutions are here if you would like to look at it. Okay, so I think that's it. Any other questions at all? Okay, this is due, as you can see here, April 28th. Today is the 27th.
I thought you had it at the bottom due on Friday at midnight.
Oh, you're right. This is the last day of class. Yeah, okay, I confused myself. Thank you. Yeah, it's due at midnight on April 30th. So on the 29th, which is the Thursday, we are going to have a special office hour at this time. We don't have an officially scheduled class, but if you do have any final questions on the examination, you're welcome to meet then. Any questions on that? Okay, good. So with that, let me give my final lecture. Where's my final lecture? Oh, there it is. Nope. There it is, Gaussian random processes. I did in this last lecture want to go through Gaussian random processes. It's a relatively short lecture, but it shows something very interesting. And we've alluded to this before, that in all cases, all stochastic processes that are stationary in the strict sense are also stationary in the wide sense. You have strict, a very small subset. You have wide sense, sloppy stationarity, if you will. That's much more broad. There is one stochastic process where they are both one and the same. If it's stationary in the wide sense, it's stationary in the strict sense. If it's stationary in the strict sense, it is stationary in the wide sense. So it's, and that's the Gaussian random process. Again, it seems that there's always, in different fields, there are certain functions that are our friends. I think in probability and stochastic processes, it's the Gaussian. We have the Gaussian random process that we're going to talk about now. Everybody talks about Gaussian noise. We saw Gaussian pop up in the central limit theorem, and it's just our overall friend. There's a whole calculus which is based on Gaussian stochastic processes called Ito calculus, ITO. And Ito calculus is the way you can manipulate Gaussian processes and still maintain the Gaussian process character. And Ito calculus was used in the solution of the Black-Scholes equation that we talked about in finance, where they started with that stochastic differential equation, where it was assumed that things were Gaussian in the random walk problem. And then the Ito calculus was applied, and lo and behold, you got the good answer. It's also used, I've seen it used in control theory where they have Gaussian processes. Unfortunately, it is such a friend that it is abused a lot. In the stock market, the movement of stocks with zero, if there's a constant volatility, the movement of the stocks is not Gaussian. The tails are much broader, as I've been told. And same thing for control theory. Usually the noise you have isn't exactly Gaussian, but boy, you can get a lot of analytic mileage out of being a Gaussian. In the area of signal processing, I would say there's a couple functions that are our friends. One's the Dirac delta, because it just gets rid of integrals. And the other one is the sinc. The sinc does kind of weird stuff, and it's very useful. It's applied, as we saw here, in the sampling theorem, and it has application in low pass filters, and it's just ubiquitous. So let's talk about Gaussian random processes. And here we have this is the probability density function for a k-dimensional Gaussian probability density function. So this is a Gaussian probability density function in small k dimensions. Now, don't confuse this with the upper value of k. The upper value of k is the autocovariance matrix. And we have talked about the autocovariance matrix previously. The autocovariance matrix is something which you can generate from statistical data. You can use ensembles. In fact, that was one of your, man, that is really weird. Now you see it, now you don't, okay. You can use ensembles, for example, to estimate, using the law of large numbers, the autocovariance matrix, capital K. And you'll notice that this has a K inverse. Where's that K inverse? Well, if you remember in the original definition of the Gaussian, what was it? It was, what was a probability density function? It was 1 over the square root of 2 pi sigma and I'm going to do here the square root of sigma squared for a reason I'll show you in a minute. E to the minus x minus the mean squared over 2 sigma squared, right? This was the original Gaussian function. Well, you notice that we can't take 1 over a matrix, that we do have to do the inverse. So instead of doing the 1 over the square root of sigma squared, we have down here the determinant. The magnitude corresponds to the determinant of the autocovariance matrix raised to the 1/2 power. Like we're doing up here, we're taking the square root of the variance. And then up here in the denominator for the regular Gaussian, we have the 1 over sigma squared. Well, we can't take 1 over sigma squared, but we can invert it. And so we do this K inverse, and that's kind of like the substitute for the 1 over 2 sigma squared. And so we see kind of a, I don't know, at least a friendly relationship between our old one-dimensional friend, the Gaussian, and the multidimensional case. M, of course, is the mean of the stochastic process. And typically, if you have a stochastic process like this, have we talked about where the mean is? We have the mean in the x direction. If this is x and this is y, hopefully you can make out my 3-dimensional sketch here. If this is x and this is y, then the mean lies at m sub x and m sub y. That's where the mean is at, right? Notice that the mean in 2 dimensions is just like it is in 1. If you took this and made it out of paper mache and you wanted to look at one point on the board where you could perform the balancing, it would be at the mean, right? If you put your finger right here, that whole thing would balance on your fingertip. However, the other thing is if you put a string across here at mx, if you put a string across mx, you could also balance that probability density function, right? It'll be a little bit floppy on one side or the other, but you could balance it on a string, couldn't you? So mx is also a measure of central tendency, as is my. You could balance it on a string that's stretched in the x direction there. Okay, so that's the interpretation. And what happens in 2 dimensions, you have not only m1, m2, you have sigma 1, sigma 2, and if you remember, you have this rho, which can be interpreted as a cross correlation. We use it to get the correlation coefficient, and that tells us how the Gaussian is skewed. So if the Gaussian is elliptical in shape, the rho tells us how much that thing is tilted. You'll notice here we have the K, and all of these things are wrapped up into the K. The sigma 1, the sigma 2, the rotation, and in higher dimensions, it's the rotation of 1 dimension, the rotation of 2 dimensions. It's just, at least for me, it's too much to keep my mind on. But just recognize that all of those rotations and scales are all wrapped up in that autocovariance matrix K. Here is the characteristic function, and we'll state this without proof. The characteristic function of a multidimensional Gaussian random variable is given by the expression which is shown here. And you'll notice in 1 dimension, a Gaussian Fourier transform to another Gaussian. And we have the same sort of thing here. We have this Gaussian transforming to this other Gaussian, if you will. In other words, this involves a lot of omega 1 squared, omega 1 times omega 3, and a bunch of other things. And this K, this autocovariance matrix, tells us the weight in these different values. And this, of course, is the vector of means in X, Y, and Z. So that is the probability density function and the characteristic function of a multivariate Gaussian probability density function. There's no assumptions here. It turns out that if you assume, and I will mention this, where'd you go? There you went. Okay. That if you did assume that K is equal to sigma 1, sigma 2, sigma K, 0 on both sides, then what does that tell you? It tells you there's no cross variances. And if we have all of this, if we have this diagonal matrix, then all of the elements in the Gaussian random variable are independent of each other. Because if you have just a diagonal row, then you can take this expression. What's K inverse? It's, well, I've written there. I don't understand how this works. K inverse in this case would be 1 over sigma 1, 1 over sigma 2, all the way down to 1 over sigma K. And that would be the inverse, and that would be zeros on both sides. But this would be the inverse of the autocovariance matrix. If all of the sigmas are the same, if the sigma, let me do it up here. If the sigma sub n are all equal to the same sigmas, in other words, all the elements on the diagonal are the same, and the means are all the same, then these random variables, these Gaussian random variables, are going to be IID. So the sigma n's, if they're all equal to each other, then you're going to get IID random variables. Okay. So this is interesting and is the multidimensional extension of the Gaussian random variable in the most general sense, where there is cross correlation among all of the random variables. Now, if we expand the characteristic function, we get the following result. We're taking this matrix vector multiply, if you will, and we are writing it out as the summation. So this would be the exact summation that you would do if you took this K and you took the omegas over here and you took the omega transpose here. And you did all of the multiplications that you need to do. You know how you do it, boom, 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 as you multiply matrices. If we were to do all of this, then we would get the relationship which is shown here. And same thing for the means. If we were to take this inner product and we were to write it out, we would get this result. Okay, so this is all well and good. Let's go on differently. Now, why are we interested in the multivariate Gaussian random variable? Well, you remember that in the definition of stationarity in the strict sense, we should be able to take any k values of a stochastic process. This is x of t. We should be able to take any k of these values and we should get a multidimensional Gaussian bivariate or a multidimensional Gaussian random variable, right? That was the definition of Gaussian random variable. So if we take 4 of them, we get a 4-dimensional multivariate Gaussian random variable. If we take 20 samples, we get 20-dimensional Gaussian random variables. This was the definition of a Gaussian random variable. No matter where we took the samples, that it would be a multivariate Gaussian random variable. Now, clearly, if it's if we choose the points, the samples at different points, the multivariate Gaussian is going to be different. If it's stationary in some sense, if we move all these over a certain amount, if we move these samples over and we retake them, then all of the samples of the shifted version should have the same multivariate Gaussian random variable, right? That's the assumption of stationarity. But this is stationarity in the strict sense. So let's see what damage we can do here. Here is the theorem which we propose. And this is pretty cool. If a Gaussian random process is wide sense stationary, then it is also stationary in the strict sense. Again, the backward arrow from strict sense stationary to wide sense stationary always applies, but in the Gaussian, they are the same. And here is kind of the proof, if you will. The proof is the expected value of x of t is equal to the mean, so the expected value of all the different points are exactly the same if it's a stationary. And here is the kicker. The autocovariance matrix is just a function of the separation between t and tau. This is the assumption of wide sense stationarity. If we have wide sense stationarity, the autocovariance is only a function of t minus tau. That means that all of the elements in the autocovariance matrix are a function of t minus tau. And as long as the separation between t minus tau remains the same, you're going to get exactly the same autocovariance matrix. So if we look at all of the points, all of the k points in the sample, we find that the autocovariance matrix is equal to this. It's the autocovariance between the 2 points at a time. We take all the points two at a time. So if we have k samples, there's k different ways where we can mix samples, x1, x2, x1, x3, x1, x4, and then x2, 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 and we're going to have symmetry, of course. But the interesting result is that the autocovariance, since we have a wide sense stationary stochastic process, is just a function of the distance between the 2 points. And that distance between the 2 points, as long as that remains the same, we're going to get the same result. So if it's wide sense stationary, then this is always going to give us the same result if it's wide sense stationary. And we find out for the case of the Gaussian, since we have to know the autocovariance, then this is exactly the same as the autocovariance we need to characterize the signal. So here is kind of a fancy way of doing it. Here is the autocovariance matrix at least from the characteristic function point of view. We could have done this from the probability density function, but here we don't have to deal with the inverse of the autocovariance matrix. So the nth element of the autocovariance matrix is equal to the autocovariance of the stochastic process, which we can compute for the wide sense stationary assumption. And it's just a function of T sub n minus T sub m. So this is totally invariant to the shift. And so we see that we get the wide sense stationary playing a role in determining strict sense stationary for this Gaussian stochastic process. If we shift these 2 points, say, for example, we're looking at T sub n and T sub m, and we shift them over to, well, let's do, I did them backwards. Let me do the T sub n over here and the T sub m over here. If we shift these backwards to minus tau, in other words, we shift this point here and we shift this point here. And these are points, of course, on the stochastic process. But if we flip this point here to here, and this should be tau sub n minus tau. If we shift this point from here to here and this point from here to here, we're going to get exactly the same result. This, by the wide sense stationary assumption, is the same thing as C sub x of T sub n, T sub m, by the wide sense stationary. And by using that principle from the wide sense stationary stochastic process, we are then showing that that if we were to shift all of these samples, we get exactly the same before and after the shift in terms of the probability density function. And the only thing that we have to impose is that the Gaussian process is stationary in the wide sense. So that is the proof, if you will. So again, this kind of illustrates the difference between, this illustrates the utility of assuming Gaussian stochastic processes. If you can assume or you can prove that it's stationary in the wide sense, you also know that it's stationary in the strict sense. And we didn't do it in here, but you might imagine that if we have stationarity in the strict sense, there's a lot more things we can do and a lot more theorems and stuff we can apply to the stochastic process for other advanced applications. So all of that is to show, again, I think I've said it 50 million times, but all of this is to show that if we have wide sense stationary for a stochastic process that's Gaussian, it is also stationary in the strict sense. Any questions at all?
I have a question it's a little bit of a tangent, but it has to do with wide sense stationary processes.
Sure.
So I was thinking, I've done some work with like GPS receivers, and you get kind of this point cloud of position solutions over time. And if you were to plot the distribution of those solutions, you did a Gaussian, usually in 3-dimensional space. There's a little bit of error in this direction, and a little bit,
But okay, but you're only getting a 1-dimensional Gaussian, right?
I think if you have your 3-dimensional position, X, Y, Z coordinates,
right,
you would be able to get a 3-dimensional Gaussian, I think, is the way I've understood it. But my question was, some processes that we deal with don't drift very quickly over time. Like the mean of your GPS position might drift slightly over months and years.
Yes.
When you run into things like that in the real world, would you just assume that over your time scale of your application that it is wide sense stationary?
Well, one of the things that you need to do is realize the limitation of the models. Don't forget, in theory and reality are the same, but in reality they're not. And the question you pose is a very important one. you have no signal that has existed forever and is stationary from minus infinity up to now. It doesn't exist. It would have to, the signal would have had to start at the Genesis creation or the Big Bang, depending on where you want to go. But here is a common assumption of stationarity in the sense that there is an interval over which a signal is stationary. In fact, if you go back to linear time invariant systems, there is an interval that the system is linear time invariant. Because after a while, you go for 50 years, that system is going to get decayed. It's going to grow mold on the resistors and begin to fade, and it's begun to change. So the best way that you can do that and apply this directly, or I shouldn't say the best, but certainly the easiest, is to assume over a specific interval of time that you have a stationary stochastic process. One of the examples, for example, is in speech recognition. And for example, when I sing, and I'm not going to sing, yeah, I am going to sing for you, but if you sing row, row, row your boat, you notice that the vowels, and singers always sing vowels, unless you're a country music singer, and then you sing R's sometime when you go, but even the R's are kind of that way. But most singers sing vowels, don't they? It's usually a oh, something like that. I think that over that small interval where they're pronouncing a vowel, that's a very nice stationary signal, right? But it doesn't last very long. It doesn't last very long, but there's lots of wiggles in that process where maybe you could cull it out and call it a stationary stochastic process within that interval. So I think that's the question you have. Now, once you have a signal that is, I would call it variation limited. In other words, it's a slow variation in the process. An example, for example, is Poisson processes. You know that the cars going by on University Avenue are not a stationary stochastic process. You are going to have fewer cars going by at night than you do during rush hour, right? So what you can do there is you can look at the stochastic process and see if you could parameterize it in some fashion. For the Poisson process, you would have a stochastic process which had a lambda. You remember the lambda, which is the average number of occurrences per second? And that lambda is going to increase, and it's going to, whoa, what's that in my head? Ooh, it looks like I have a polyp. Okay, that process is going to increase, and it's going to go up to rush hour. And then as rush hour goes down, that lambda, that average number of occurrences per second, is going to go down. So it's no longer stationary, but if you look at a piecewise constant piece of that, it is in essence a stationary stochastic process. So that would be the example I would, that would be an explanation I would offer. I also noticed when a long time ago I did use of neural networks in forecasting power loads. And when you forecast power loads, you look at previous data and you use that to train the neural network to figure out what the power load demand is going to be the following day, right? And you have all of this historical data. Well, the problem is that if you go back 10 or 20 years, the way that civilization is increasing, especially around Waco and stuff, there's more houses, there's going to be more people, the power consumption is going to be more. And so you have to figure out what to do with that data that's been like 10 years old. How do you throw it away? Is it still usable? Can you discount it in some sort of fashion? So these are the questions that one must ask when you have a variation limited stochastic process, one that is changing slowly with respect to time. Even in power load forecasting, you have seasonal variations, don't you? You have from the summer to the fall, to the winter, to the spring. You have a variation limited. Now that's an example that we talked about. You can either talk about it in terms of a variation limited signal, or you could model it as a cyclostationary stochastic process, right? Because those wiggles this year would be the same as the wiggles the next year, except they would be off by a stochastic process. So A lot of this is looking at the problem that you have, applying your domain expertise, realizing that one size does not fit all, applying your engineering expertise and all the tools in your toolbox. And hopefully we put a lot of tools in your toolbox in this course, and then applying those tools to the problem that you have in front of you. So I hope that helps. Does that help, Theo?
Yes, thank you. It was helpful to talk through the idea that there's often no such thing as a perfectly wide sense stationary process, but we could have a slowly changing one. And I think I understand what you were saying about the one-dimensional distribution. If you were only taking the measurement of your distance to a single satellite, I think you're right. That would be a one-dimensional Gaussian.
And well, no, it'll be one dimension, but you have to look at the entire stochastic process. You have to look at the entire stochastic process and sample it at 50 different places. And that gives you the wide sense stationary. You can't sample it at a single point.
That makes sense.
The other thing I would mention, you talked about higher dimensions. We can have higher dimensional stochastic process. For example, if you were to look at during rain and you were to have a little detector, a little board that saw a raindrop go plop, 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 right? You would have a two-dimensional stochastic process. And that two-dimensional stochastic process would have to ramp up into a multidimensional systems analysis then. It does turn out, by the way, it's Poisson. It's still Poisson with the rain hitting. So if you just go by the audio with the rain hitting, you go plop, 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 which is a Poisson process. I think a good model for that is a Poisson process. But if you do it in 2 dimensions and actually look at the spatial coordinate where the raindrop lands, you are going to have a 2-dimensional Poisson process, aren't you? Okay. And likewise, you can have 3 dimensions. You can have multidimensional stochastic processes. For example, the image you're looking at right now, me, right, with all my colors going great behind me. What dimension of a signal am I? This, by the way, is in some of the introductory remarks to multidimensional signal processing.
Is it 3 dimensions because there's 3 colors, red, green, blue?
No, you're close. You're close with it. It's 3. Okay, a black and white image is a 2-dimensional image. So if you think about an image that you divide it up into pixels, each one goes to 8 bits, 0 to 255 or something like that. At each point, you have a value. So a function is where you assign a value to each point in the system. So when you're looking at me, you're actually seeing 3 one-dimensional images. You're seeing the red image, the green image, and the blue image. So there's 3-dimensional images. I'm sorry. There's you have 3 2-dimensional images. 3 2-dimensional images. And I didn't really catch the problem you were looking at, but it sounded like you had more than 1-dimensional image. So you have to apply higher order statistics to those. Okay.
Thank you.
Okay, good. Good question. Good question. Because one of the things you'll find as you go out and you look at problems, again, you have tools in your tool chest, and that's what we do as engineering. As engineers, we have tools in our tool chest that we can grab onto. And it turns out that we didn't have time to go through all of the different scenarios, but hopefully this will give you an idea of where to go if you need additional information. That's the reason when I give you grades, I'm not really interested in any equations that you've memorized or something like that. When you come up with a problem, this is just kind of my philosophy. When you come up with a problem as an engineer, you go, oh, I remember that. Let's see I know where to go to look for the solution, and that you can appeal to the solution, and you don't have to have all the equations off the top of your head. You have to apply your domain expertise, bring together your domain expertise in order to apply it to solving the problem. So, Okay, any additional questions at all? Okay, let me ask you some questions. This has been a totally remote class. I have not met with you guys in person. I'm just wondering what you thought about the class content and ways that it could be done better. I think we're probably going to go back to nose classes in next semester, not in the summer, but in the fall semester. That'll be my hunch. But any comments on the course content at all?
Having taken both your in-person and your online classes now, I think they are pretty comparable in terms of like getting the content across. I think the biggest kind of drawback with the online ones has kind of just been the marker and tablet you have, how sometimes it does weird things, but
I still have a master that's this stupid thing. See, it doesn't even show up. It's ashamed. It's ashamed of its operation. It won't even show up. Okay. Okay, well, that's good. That's good. Often people say that let me offer you this. Often they say we spend too much time on the introductory material because it's material that you've had already. Did you find that the case in this course? No? Oh, okay.
I don't think we spent too long. We spent like maybe a week or 10 days, and then it seemed like we were off to kind of new stuff.
Okay. Okay, that's good. I hope it also tied together some of the things that you looked at in statistics where you did like chi-squared tests and stuff. And I remember when I took it, I used to think, where did that come from? You know, the chi-squared thing. But hopefully you know about these things right now. It's going to offer you a final in the exam where you generated the T statistic, you know, the one that Gaussian did, where you have a Gaussian assumption and you do very low samples. And that can be derived with the material that you have now too, just like the chi-squared, but I decided not to. So, okay, guys, this is really good. We're a little bit early. We will have a office hours in 2 days, and please come with your questions about the final examination or any other thing that you have to talk about in the course. And that's it. And since you bet on it, until next time, be of good cheer.
Dr. Marks?
Yeah.
Can I stay and talk to you?
Yeah, you can stay. Okay, I'm going to
okay.
stop recording, guys.